Welcome to today's webinar titled Implementation and Accuracy of Doppler Navigation with LEO Satellites, based on a paper published in the summer 2024 issue of Navigation, the Journal of the Institute of Navigation. This paper can be accessed from the Navigation Open Access website at navi.ion.org, where you can read, download, cite, and share this article and many others. Today's webinar is presented by Ariel Barron. Ariel Barron is an aerospace engineer with a background in navigation systems. He holds a Bachelor of Science in Aerospace Engineering from the University of Maryland and a Master of Science in Aerospace Engineering from the Technion Israel Institute of Technology. Today's webinar is being recorded and will be available on our website, YouTube, and other social media channels. Following the presentation, we will accept questions from the audience. You can submit your questions by selecting the Q&A button in your viewer. Now, thank you for joining us. We will turn the time over to Ariel.
Thanks for participating in this webinar today on our paper recently published in the summer issue of Navigation called Implementation and Accuracy of Doppler Navigation with LEO Satellites. My name is Ariel. This work was done by myself and Professor Pini Gorfil from the Technion and Dr. Hector Rothstein from Rafael Advanced Systems. So I'm going to be giving an introduction, a general framework, and some of the research that was done in this paper. I'll give a general framework, and I'll show where our research has kind of built in into the work that's already been done in this area. We, in this paper, cover the area of LEO navigation. This is an area where we'd be using LEO satellites, which have the advantage of being 20 to 25 times closer to the Earth, so having a stronger signal, which means you might be able to receive them indoors or in foliage type environments. And there are also a lot more of them. We've seen recent constellations like Starlink and Kepler and others from Amazon launched recently, and there are quite a lot of them that are orbiting around us. So we'd like to use these signals that are coming from these satellites for navigation purposes, or opportunistically, or in a SOOP fashion, or signal of opportunity. And in this area, this paper, we're using external ephemerides, and we're only using the Doppler-shift from these signals as the measurement observable. So we have a figure here of kind of the area we're working in. We have satellites, and they're sending us their Doppler-shift, and we get TLEs or orbital data from an external source like a ground station, and we have a LEO receiver, and we're solving for our position, our clock bias, our velocity, and our clock bias rate. So before I go on, I'll kind of talk about some of the work that's been done in this area. Here, if we look at the area of LEO navigation, we can kind of divide it in two areas. One is tailored broadband satellites that are actually built to be used for navigation, and that's less the area that we're focusing on. That's kind of that work has been done by Reed, and that's in what became today the startup called Zona Space Systems. We're more interested in using signals that come from satellites in an opportunistic motion. And so there's been a lot of work done. Some people like Dr. Humphreys at University of Texas has looked at using pseudo-range or time of arrival signals. Others have looked at using carrier phase or with base station and fixing ambiguities. Or either by standalone or actually solving for the ambiguities. Others further have looked at both using pseudo ranges and Doppler shifts. There's also been work in frequency difference overall. But in this paper, we're specifically looking at just using the Doppler shift. which makes a very easy receiver to build. Um, and uh, and also in this area, there's been a lot of work. There's been measurement models by Benzero and Morales-Fair and Cassis. And we're specifically building in this paper on the work and the measurement model used by Dr. Psyche. Um, so um, so that measurement model is novel because it relates the Doppler shift to the finite difference of accumulated delta range instead of using pseudo range rate. This model was developed kind of to not neglect ionosphere and tropospheric terms. And while other models have looked at Doppler navigation, just using using Doppler observables, they do not only use Doppler observables. They sometimes integrate them with pseudo ranges or carrier phase differencing from base stations. So before we go further, I'll just give a short reminder what is an accumulated delta range. So in most receivers of the super heterodyne type, we look at their front end. If you have a transmitting frequency from the satellite, and you have a received frequency on that in your receiver, and they're being mixed, and you get a beat frequency at the receiver, and you count the cycles, and each cycle has this associated wavelength, and you sum those up or accumulate them. That's the range that's been accumulated over a period of time. We call that the accumulated delta range, or the ADR. So again, this measurement model is one of the first to only use Doppler shifts with no reliance on additional sensors. The Doppler shift is not only dependent on it's dependent on position and clock bias, but also velocity and clock bias rate. So this dependence on Doppler shift on these parameters allow us with 8 satellites to be able to solve for our whole state. We need 3 for position, 3 for velocity, and another 2 for clock bias and clock bias rate. And that can only happen in today's modern LEO constellations. So this measurement model was again developed by Psyche in his Transit on Steroids paper in 2021. And it's harkens back to the original transit system. So in this model, we relate the Doppler shift here, dj, to the derivative of the accumulated delta range. So this is the equation here for the accumulated delta range. And as you can see, it looks a lot like a pseudo range. It's the user position minus the satellite position and the norm of that. But it's different from a pseudo range in this measurement model because we notice here that the ionosphere is being subtracted because the ionosphere delay is in advance rather than in delay because it's a carrier phase measurement, not a forward measurement. So this lambda here is the wavelength. And if we measure these Doppler shifts and we multiply it by the known wavelength, we have a relationship between our measurements and a measurement model, and we can solve for our state, again, being position, velocity, and clock range. So Psyche approximate this derivative via finite difference. So this is a 5-point finite difference that is our measurement model essentially. And this delta TR is the parameter that we use in our finite difference. Seeing good results, between 0.1 and 0.5. And so measuring Doppler shifts, and with this measurement model, we should be able to solve for our desired state. And we can do that in the form of a least squares problem. So y here is our measure. We take the Doppler shifts, we multiply them by the wavelength. I call this the range rate equivalent Doppler shifts. We put them in this y vector right here, and then this h vector function is our finite difference of accumulated delta range, and this relates our measurements to our desired state. And this is a nonlinearly squares problem, and we can solve for our desired state using a gradient descent type method. And we would do that in order to reduce this cost function that we have here. So this cost function is here. There's the measurement noise right here. These are range weight equivalent Doppler shifts, and this is our measurement model. And we'd want to find a state that minimizes this. So this kind of should sound familiar to basically standalone GPS, and it is. We've summarized the algorithm from that 2021 paper, and we've named it the Psyche batch filter. And it looks a lot like a standalone batch least squares filter that you would use for solving a standalone GPS problem. So you would have like an initial state, and you would compute a measurement model, and you would kind of put your measurements in your measurement model in a vector, and you continuously calculate the corrections to that initial guess until your cost function is minimized. You would do that with a gradient descent type method. So again, this looks a lot like GPS, but just like in GPS, in order to do that, you need a Jacobian matrix. And so one of the things that we've gone ahead and done in this paper, while this Jacobian is outlined in the Psyche paper, we actually went ahead and derived it. And the full derivation is in the paper, and it can be found there. So if you were to run this batch filter, it kind of looks like this. This is one of the simulations you run. You start with a high cost, and as the iterations go on, your cost gets lower, and you solve for your desired parameters. So you need an initial guess, and in GPS, the great thing is that it's globally convergent. You really don't have to know where to start. You can use an initial location that's very far away. And one of the things we investigated in our research is, can we do the same thing with this Psyche batch filter? And the answer is yes. We can get it to converge from the center of the Earth or no previously known location, but with a caveat that it's not always true. So you can, but not always. So like we said, this is the analytical Jacobian that we derived, and here it is in condensed form. And we've provided the derivation and the equations in the paper. So one should be able to take this paper and go in and implement a Psyche batch filter with this Jacobian. It's difficult to derive, and it's also difficult to implement. So we asked the question if a Jacobian matrix based on a simpler Doppler-shift model would be able to be used with this Psyche batch filter. So here's a very simple Doppler-shift model, and this would be its associated Jacobian. And this model, this Jacobian, was originally used in the Psyche paper to do GDOP simulation, but we asked the question if we could take this Jacobian here and use it actually in the batch filter. And we did, and we were able to do that. And we've outlined expressions for, this is the unit vector rate between the satellite and the receiver. So we've outlined expressions for that. And this is the acceleration between the satellite and the receiver. And we also outlined expressions for that in the paper. So we have gotten this one to converge. And so our next natural question was, well, which one is better? So in the paper, we did a comparison of 3 Jacobians. One is the analytical Jacobian that derived. The other is the simplified Jacobian. And the third one is just a numerical Jacobian. And we did a Monte Carlo simulation for that, and the results for that are also the paper. So an important question for these types of systems is dilution of precision. So um, they help us answer the question, given a measurement noise on a Doppler-shift in hertz and then convert it over to meters per second, what would be our expected accuracy on a for a desired state parameter, whether that be a position or a velocity or a clock parameters. So so we can see this kind of should look a bit also similar to GPS. So these are kind of, we would say, our uncertainty in our state parameters. These are our measurements. And if we relate these two, we should be able to get dilution of precision. So this, a lot of this formulation has been done in the Psyche paper. Our developments here are that we use the analytical Jacobian matrix to compute dilution of precision. So, so in order to do this, there are a couple of rules for dilution of precision. And so a GDOP analysis requires that all of the Jacobian or coefficient matrix be non-dimensional. It also requires that all the estimation errors have the same units and that those units are identical to the units of the measurement errors. So if the measurements are range rate equivalent Doppler shifts or carrier phase times the Doppler shift or wavelength times the Doppler shift, so that unit is in meters per second. Therefore, our measurement errors should also be in meters per second. And because of the first rule here, our Jacobian matrix should be non-dimensional. So that means that we have to convert all our measurement errors to meters per second, and we have to rescale those error space so that they're meters per second. We also have to simultaneously divide the corresponding column in the Jacobian matrix so it's non-dimensional. So if we look at delta R dot, this is our clock bias rate. It's in 1/2. So if we just multiply that one by C, we have meters per second. But we also, so that would mean that we have to take the last column of the Jacobian and divide it by C. That one's simple. Delta R is in meters though. So we'd have to, it's more complicated for that. So if we look at this Jacobian, this is the derivative of the line of sight, or line of sight rate. And so a reasonable approach that Psyche takes is to divide it through by its maximum value, so that it's scaled through, and so that this is non-dimensional. So that maximum value happens to be something called the line of sight sweep rate, and that's derived in that Psyche paper. And so for our delta R, all we have to do is scale, divide the column in the Jacobians by this gamma, and then multiply it over in the state. So lastly, we have to also take care of just the clock bias. So if we again look at this Jacobian, this is the acceleration between the satellite and the receiver. So we using the same, so that we just take the acceleration, maximum acceleration that the satellite can experience, then and divide it through here and multiply it here, then we're able to deal with the dimensionality issue. So this is the maximum acceleration, also derived in that Psyche paper, and that's the scaling parameter for this. And delta V is very easy because it doesn't require any scaling. It's already in meters per second. So um, so um, my screen. You can still see my screen here. Yeah. So if we continue, if we do this operation. So we take this gamma here, divide it through here, and take the eta and divide it through here. And this is our dilution of precision matrix. And we went ahead and did this on the actual Jacobian needed for the bridge filter. So just in order to get the GDOP, the actual total geometric dilution of precision, you would take this matrix, take the transpose, and multiply it by itself, and then take the trace. So in the end, what we're expecting to get here is sort of a relation. If we have a measurement noise on a Doppler-shift, and we have in our paper we give the dilution of precision parameters for the individual state members. It's also something that we provide. So if we just are interested in position or just interested in clock bias and velocity. So if we take the measurement noise and multiply it by the position dilution of precision, this would be our estimated precision that we would get in position. Similarly for clock bias, and similarly for velocity and clock bias rate. Now, we can see through these relations that in order to get a good estimated precision, we would take we would need our measurement noise to be small, and our geometric or dilution of precision parameter to be small. But we'd also need a larger gamma and eta. So these are the good property that Leo constellations have is that they're larger for them, and this system does not work well with GNSS because those are smaller, and so going through these, you would get a worse precision for the same measurement noise in a GNSS constellation or a MEO constellation than you would get in a Leo constellation. So we went ahead and simulated this. And we used MATLAB's satellite communication toolbox, and we simulated a ground location at a known time and place, and we simulated satellites with TLEs, and we put all those parameters in the GDOT matrix, and we were able to get estimated HDOT values for various constellations. So we looked at just using regular GPS, and then all of GNSS. We looked at Starlink. When I say all of GNSS, I mean Galileo, Baidu, GLONASS, etc. This is Starlink. There's OneWeb, which is also Leo, Global Star, and a constellation called Sun. So if we went through this simulation, and this is the mean horizontal dilution of precision for position. And if we take a 0.1 meters per second measurement noise, which some have told me is conservative, and others have told me that it's too low. But real hardware tests will tell the tale. But anyway, if you take this measurement noise and multiply it by the GDOT the HDOT that you have and divide through the associated gamma eta here, then you would get these predicted accuracy in these constellations. So for GPS, you're getting a predicted accuracy of 11 kilometers. For all of GPS, it's down to 600 meters. And Starlink, it's 13 meters, and OneWeb 100 meters. And again, so this is associated with the 0.1 meters per second noise figure. If that noise figure is reduced by an order of magnitude, then all of these numbers would also go down by an order of magnitude. So work should be hopefully done in the future Leo receivers to reduce that measurement noise. The last thing that we had to look at is actually implementing the Psyche batch filter. And we basically, again, used the MATLAB satellite communication toolbox, and we simulated these Doppler shifts or ADR rates, and we just simply added noise of 0.1 meters per second. So we also model clockwise and clockwise strips, and we check what our batch filter outputs, and we compare it to the ground truth location that we used in order to generate those measurements in the simulation. So if we look here, this is the measurement noise on GPS and all GNSS. These are the same constellations that we checked out for the dilution of precision simulation. With these same measurement noise values, we're getting values in the batch filter simulation that are on the same order of magnitude as what the dilution of precision simulation gave. So here we're getting on the order of kilometers, and all GNSS is getting in the order of hundreds of meters, and Starlink is around 10 meters. And these are the figures for the other constellations. So again, here, if we would have just reduced our measurement noise or been able to, then all of this would reduce by an order of magnitude. Okay, yeah, so that concludes most of or what's included in the paper during this research. So what can be done in the future in this area is actually go in and build a real LEO receiver and test its Jacobian and its patch filter on a real LEO receiver getting real signals. Additionally, more research should be done into minimizing the residual between a range rate equivalent Doppler-shift and your measurement model, which is your cumulative delta range rate for other Starlink LEO data. What that means is looking at the influence of clock bias rates and how good does our estimate of the satellite's orbit need to be in order to get good residuals. Can the orbit be off by hundreds of meters or kilometers in the case that you would be using TLEs in opportunistic fashion and still be able to get good results? Additionally, it might be prudent to have a look at simultaneously estimated satellite clock bias rate. Since in LEO constellations, you don't always have that given, like in GPS or GNSS, where they're broadcasting their ephemerides. And also, another option would be to model those clock bias rates for LEO satellites. And further, you could look at doing dynamic tests or using inertial sensing and integrating that with this batch filter, and using different estimation techniques, whether that be a Kalman or particle filter formulation, and changing it over from a batch filter to one of those estimation techniques. Yes, so this concludes this presentation. Were there be any questions?
Thank you, Ariel, for the great presentation. We'll now accept questions from the audience. As a reminder, you can submit your question using the Q&A button in your viewer. And it looks like we already have some questions coming through, so we can go ahead and start reading those off. Let's start with this one. What are some of the weaknesses of using this LEO PNT method?
Sure. Great question. So some of the weaknesses that have been observed are that there's not such good dilution of precision for the clock parameter, the clock bias. So there's been, while the position and the velocity are better, the clock parameters themselves are not as good. So there's been further work done by Brian McLemore and Dr. Psyche at looking at integrating Doppler or pseudo ranges with these Doppler shifts, and that appears to help the dilution of precision related to clock parameters.
Okay, thank you. Next question. What is the impact in the final accuracy of the user position using a TLE? As this format is well known to be quite inaccurate, in the order of, km for the position of HT satellite.
Sure. So, yeah, that's correct. TLEs are not good. Um, at epoch, they can be kilometers off, and then they just increase. They're not quite good. Um, so there's an open question of what type of error uh, is present in the TLE. So if the TLE is most of the error that's present in the TLE is that the bias types, then the differentiation that happens in the accumulated delta in the when we're deriving the accumulated delta range kind of and doing a finite difference cancels out that bias. But so in short, if we're able to find the type of error that's present in TLE, then it helps us know how feasibly this can be used with TLEs. But uh, what has been done in that Psyche paper is that the TLEs themselves or the ephemerized themselves are disturbed. So he adds a bit of uncertainty to the satellite positions, and he does a simulation in that paper to check out what the influence is on the user position.
Okay, next question. Are your measurements considered ionosphere free, or do you use an ionospheric model? If so, which model?
Um, so so should stress again that these simulations these are just simulations where we in this work we didn't um, actually use the Leo receiver. So, but in our accumulated delta range model, we did use the Klobuchar model for the ionosphere, and and the whole reason uh, this this model was developed by Psyche was in order to take into account um, the influence of ionosphere and troposphere on Doppler shifts. So we use Klobuchar, and if it's a good question to ask what's the acceptable difference between using a Klobuchar model and what the actual measurements of Doppler shifts would be. What would be the difference in that measurement residual? So if someone builds a Leo receiver and measures a Doppler shift and then uses a Klobuchar model, that would be a good area to investigate.
Thank you. Okay, next question. For future developments, how do you envision the ephemeris data so the receiver can calculate the position solution?
How do I envision? Sorry, what?
Let me see here. For future developments, how do you envision the ephemeris data?
Oh, okay, yes. Yeah. Yeah, so this is a kind of harkening back to the earlier question. So right now you'd be using an opportunistic fashion TLEs, but in order to make this system work well, it should be investigated as well. A ground station network would improve the positions of the satellites um, and and how that could impact the solution. So first step would be looking at how bad can we get away with to still use this solution, and then someone should build a ground network that would meet those requirements.
Okay, let's take a look here. We have a couple more. Um, maybe you've already touched on this a little. What is the impact of signal frequency on the accuracy of this method?
Um, so in simulation, there's no um, impact. In a real system, you would have an impact because you're using a certain wavelength and frequency in your measurement model and your Doppler shift, and if they don't agree, then your residuals would be off. So and frequency can of the satellite signal can change for various reasons. The short answer is that it could affect your measurement residual.
Okay, I think we have time for maybe one or two more. Do you need Starlink's Dishy to perform navigation, or can you use an omnidirectional listener?
Um, yeah, so again, this work it does not build a Leo receiver, but they're not that hard to build. And so you can, there are various resources online to go in and build something and you don't need a Starlink dish in order to do that. With not that much work, you'd be able to build the receiver and start getting Doppler shifts and implementing this method.
Okay, let's do one more. Okay, someone's wondering, why is this high DOP and 2D position values for GPS and GNSS? What were the simulation parameters in this regard? They mean like how many GNSS satellites were visible.
Sure. There are many satellites visible in GNSS. You get um, 16 or so just from GPS and Galileo. Problem that causes the dilution of precision to be higher is that those beta and gamma values that we derived are smaller for those constellations relative to Leo constellations. So they increase the DOP because the original DOP is divided by those beta and gamma. And so you end up getting a worse solution, a worse DOP, because of the physical properties. And that kind of makes sense because we're using Doppler shifts and GPS are slower moving satellites. MEO orbits are slower moving relative to us. And so it makes sense that they have these smaller physical scanning data.
Okay, we do have three more questions. I think that's it. Ariel, if you have time, do you want to do three more questions? Is that okay?
Sure.
Okay. It looks like the next one is, where does that big difference in performance come from when you compare GNSS and LEO positioning errors? Is it related to SV speed?
Yes, exactly. It's the satellite vehicle speed. Um, GPS satellites are moving slower than relative to Doppler satellites or LEO satellites, and so um, uh, intuitively, the faster they're moving, the better for us. Or the faster they're moving at different places where they're located is better for us in this concept. So that their dilution, sort of like their dilution of precision. Uh, um, Sort of like if in GPS, if they're all bunched together, they would be bad. And so the same thing in this concept, if they're all moving slowly, they would be bad.
Okay, someone's interested in knowing if you could better specify the matter of cold start initialization because some research has pointed out possible problems with LEO satellites.
Um, well, we've gotten cold start to work with the system. Uh, This is a simulation, so if the residuals are bad in a real system, then maybe cold start could be more difficult. Mathematically, we've had problems with cold start, and but we have gotten it to work in some situations. So that's the area of research, kind of where it does work and where it doesn't work. And obviously, in a real system, it's going to be hard cold start to work because the residuals will be large.
Okay, the final question. Can Doppler navigation with LEO satellites help improve coverage and resiliency for the Arctic?
For the Arctic. Well, it's I guess those would be polar satellites, and they would be in polar orbits. So uh, they're mainly how fast satellites are moving is mainly how far they are from the Earth. Lower satellites move faster, and so just because a satellite is orbiting polar region doesn't mean that, and it has the same altitude as it would have at another inclination. That doesn't mean that it's any better or any worse. It's more of a question if an operator sends a low satellite that has a high inclination orbit um, to orbit those regions. And if that happens, and enough of those happen, um, then there shouldn't be any reason that the system couldn't be used there as well.
Okay, thank you. Thank you everyone for joining us for today's webinar, and thank you, Ariel, for your time and preparation. We want to remind everyone that a recording of this webinar will be posted to our website, to our YouTube channel, and other social media channels by this Friday, the 28th. So thank you again, and we look forward to having you all join us for a future ION webinar. Thank you.
Thank you very much.